Hi, everyone. Welcome back to Intro Statistics. Today, we're going to be talking about statistics when we're just talking about one variable at a time. And then in the future, we'll talk about how to look at relationships between more than one variable. So, some of this is going to be pretty simple. You might have learned this in high school or even middle school, but it's always good to review before we dive into more complicated concepts. So, first, we want to think about how would we answer a question if somebody asks me, what is the typical value for a particular variable? Let's say I have a data set of individuals and my variable that I'm interested in is age. And someone asks me, what's the typical age of someone in your sample? And specifically, I'm going to think about if I want to answer that with just a single number, like saying, well, the typical person in my sample is around 19 years old, as opposed to giving a range. We'll come back to that idea of a range later. But for starters, we want to think about just giving a single number. Whatever we use to systematically come up with a way that we're going to answer a question like this is going to be called a measure of central tendency. In other words, measures of central tendency are built to answer questions like, what is the typical value for a given variable? So, like I said, this is probably something you've seen before, maybe in high school, the main measures of central tendency. And there's three core ones that we're going to focus on and that come up again and again and again: the mean, the median, and the mode. So let's start with the mean. The mean has another name, just the average. So it doesn't matter if you call it the mean, if you call it the average. And to calculate the mean, you're just going to add up all the values and then divide by the total number of observations. And you can see on the screen here the formula for how we do that. On the left side of the equation, you see mu, which is a Greek letter, which is typically, or one of the typical ways to represent the mean. And then on the right side of the equation, we see this summation sign, and then x, which refers to whatever variable we're computing the mean for. So if we're thinking about ages, like I said in the example a moment ago, then x would represent the variable where we record the age of each individual. And then this sub I just refers to each individual. So in other words, we're going to sum through by adding up each of the individuals, and we'll see other examples of this in the future. And then we're going to be dividing by capital N, which means the number of observations. So that's how we make sense of this formula, summing up all of the values of the variable and then dividing by the number of observations. And that gives us the mean, which we're representing as mu. Now, a second alternative measure of central tendency is the median. The median is equivalent to the 50th percentile. And we can calculate that by just lining up all the values from least to greatest for that particular variable. Again, if we're looking at age, we would say maybe the youngest, if in our data set, maybe is a 9. So we're going to put all the 9s at the bottoms, then all the 10s, then so on and so forth. Once we've got them all arranged from least to greatest, then we're going to pick the value that's in the very middle. That's the 50th percentile or the median. If two values are tied for the middle, which will happen if we have an even number of observations, then we're going to have two that are in the middle. And if those two values are different, then we're going to take the average of those two. We use the average to break ties when we're calculating the median. And finally, the mode. The mode just is the most frequently occurring value for that variable. So most of the time, we're not going to need to calculate these things by hand. We'll have software that will help us do this. So the main thing we're going to focus on is knowing how to decide how to interpret these different measures of central tendency and when one might be more useful than the other, although it is often useful to go through the practice of calculating these by hand sometimes. So we might do that outside this video. But in this particular video, we're not going to actually show an example of computing this by hand. We'll just assume that software is able to do it for us. So what are some of the pros and cons of these different measures, some of the unique characteristics? In other words, why do we need 3 different measures of central tendency instead of just settling on one? Well, it's because each of them have particular characteristics. So one thing to know about the mean or the average is that it can be very sensitive to outliers, which outliers is a word that just refers to unusually large or unusually small values. And there's not a clear definition of exactly when something counts as an outlier or when it doesn't. It's kind of like the word big. Big is a bit imprecise, right? It says that, and it's relative, right? So we can sometimes describe something as big, and it's a useful word to have as a part of our vocabulary. But it's really hard to come up with a strict threshold for something when something is big or it isn't big, right? You look at somebody's house, and one house you might say is definitely big, another one you might say is definitely small, but there's going to be a lot of gray in between, right? Like this is a little bit bigger than average, but does it count as a big house? I don't know. Same with outliers. It's going to be hard to come up with a hard and fast rule for how to define what an outlier is, although people have come up with different rules of thumb. But in general, the word outlier just refers to something that's unusually large, unusually small in our data set for a particular variable. So the mean is going to be particularly sensitive to those really big or really small values. So it can be a little bit deceptive if we have a variable where there's really big outliers. The mean might not be the ideal measure of central tendency in that case. The median, one of its big benefits is that it's not so sensitive to outliers. So when you look at data that is being reported in different government reports or academic studies on income, often people will focus more on the median income than the mean income. And the reason is that income is a variable that often has really big outliers, right? In the US, we have several people who have over $1 million in wealth, which I guess is wealth is a bit different than income, but you can imagine that a lot of those people who are billionaires are going to have really, really large incomes. Those are going to be outliers. And if we calculate the mean wealth or the mean income in the US, we're going to have those values very much being affected. The mean is going to be quite large because it's affected by those small number of individuals who have really, really large incomes. The median is going to be less sensitive. It's just going to say the point at which 50% of the population has more than that and 50% has less than that. And so it's going to give us a very nice intuitive measure of central tendency, even in a case where we have outliers. The mode, on the other hand, tends to be useful in somewhat different circumstances. So the mode is not going to be a common measure of central tendency to use with something like income, particularly because income can be measured to several digits. We could create bins like we do with a histogram and then talk about a mode based on those bins. So that there is a potential workaround here. But in general, if we have a variable that's measured to several digits, like income, then we would prefer to use the mean or the median, or at least that would be our default, rather than using the mode as our main measure of central tendency. However, the mode is going to be super useful if we have qualitative data. Sorry, I thought we had a bullet point for that, but we don't. Qualitative data, we can use the mode as a measure of central tendency, but we can't calculate the mean or the median for a qualitative variable. So that's where a case where we definitely want to use the mode. It's our only measure of central tendency out of these three if we have a qualitative variable. But for quantitative variables where we measure them to lots of digits, the mode is often not going to be very useful. Another thing to know about the mode is that there can be more than one mode. Because two different values could be tied. Let's say I'm looking at income data again. Might be that the most frequently occurring values are, let's say, in a random data set that we have, $10,000 in annual income and let's say $50,000 in annual income, because maybe there are 20 people in our sample that have $10,000 in income and 20 people in our sample that have $50,000 in income, and no other value occurs at least 20 times in the data set. So that would be an example where we have more than one mode. So that's something to know about the mode that's different from the mean and the median. There's always going to be one mean, one median, but there can be more than one mode. All right. Now we're going to talk about a different statistic, a different category of statistics, measures of spread. So just like we had a question to motivate what a measure of central tendency is, we want to have a question or two to motivate what a measure of spread is. So I might ask a question like, how tightly is the data clustered around the center of the distribution, right? Maybe I know the median income in a particular community is or the median household income is $40,000. I want to know, well, do most people in that community earn really close to $40,000, or is there a lot of variance, a lot of variety in terms of how much income people earn? Another way we could phrase this are most data points pretty close to that mean or median? The way that we're going to be able to answer a question like this is with a measure of spread. So again, there are multiple measures of spread. One of them is just to give the range, right? So maybe we say, well, the lowest earning person in this community or the lowest earning household in this community earns $0, and the highest earning household earns $250,000 a year. That would be our range. We've just said what the smallest value is, what the largest value is. And we could say, we can also describe the width of that range, right? So from 0 to $250,000 is 50,000, 250,000. So we would say that we have a total range of 250,000 from low end to the high end. Um, this can be useful, and often we will in papers and reports report the range, but it doesn't necessarily tell us about whether or not most observations are close to the mean or median. It tells us what the most extreme cases are, but it doesn't tell us much about the typical case. So one alternative that we can use, you're going to see the word range in this next measure of spread as well, but this is the interquartile range. So instead of saying the minimum and the maximum value, instead we give the 75th percentile and the 25th percentile. And often, again, we're going to subtract the upper bound from the lower bound of this, right? We're going to say if the 75th percentile is $100,000 and the 25th percentile is $25,000, then we would say $100,000 minus $25,000 is 75,000. So that's our interquartile range, how wide that interval is. But we can also just cite the top and the bottom of that range. Again, just to remind you, we talked about percentiles last week, but the 25th and 75th percentile are calculated like the median, where we line it up from smallest to largest, except that the 25th and 75th percentile are going to mark the 25% point and the 75% point within the data when it's arranged from least to greatest. Another thing to know about the interquartile range is that it corresponds directly to what we learned about in the prior lecture with box plots, right? The box part has the median indicated in the middle, and then the top and the bottom of that box are the interquartile range, the 75th and 25th percentile. And then the full range is the whiskers, right? So we see both the range and the interquartile range showing up on a box plot. Now, the most common measures of spread with quantitative variables are going to be variance and standard deviation. And I should highlight that all of these measures of spread that we're looking at are only going to apply to quantitative variables, not to qualitative variables. So variance, standard deviation, what are these? These are a little bit harder to define. So let's look. This is the equation for how to measure variance. And we're not going to talk through this in too much detail right now, but this is in words how we would try to describe what's going on in this equation. It's the average squared deviation or squared error. And another way we could say that is it's the average squared difference between each data point and the mean. If you'll recall, mu is one way to represent the mean. So that's what we have here. So we're subtracting each value of the variable from the mean of that variable. We're squaring that difference. That's why we say squared deviations or squared errors. And then we're going to add up all of those squared deviations or squared errors and then divide by the total number of observations. Well, when you add up all of your values and divide by n, you're getting an average. So we're looking at the average squared deviation. Again, that's a little bit of detail that might go over your head, but just explaining what this equation is representing. Standard deviation is going to look very similar to variance, except that now we're going to take the square root of that total equation. So you can see that before we had sigma squared. This is the Greek letter sigma. Sigma squared is how we represent variance. Well, when you take the square root of something that's squared, you just get sigma in this case, right? If you take the square root of sigma squared, you just get sigma. And that's why we're writing the standard deviation with just sigma. And again, the details of these equations are not necessarily the most important thing for you to understand or memorize. It's going to be more important for my purposes that you understand how to interpret or how to make sense, how to use a standard deviation or variance as opposed to how to calculate it yourself. But we do want to go through the equations quickly. So one way that we can interpret the standard deviation, and this is something that I like to have memorized, is that you can think of the standard deviation as telling us what is the typical distance between a data point and the mean. This is not a 100% reliable definition of the standard deviation, but this formula will give us a really good approximation of the typical distance between a data point and the mean. So if somebody asks you, what is the standard deviation? This is something you might want to memorize. The standard deviation approximates the typical distance between a data point and the mean. So in other words, if the mean is 5 and the standard deviation is 2, then you would say, well, the average case is 5, but also not everything is right at 5. On average, an observation is going to differ from 5 by about 2 points, right? Two units. So we're going to have lots of 7s, maybe lots of, a 3 would be a very typical observation because it differs by 2. And of course, there's going to be observations that are further and closer to the mean. But this is just saying, on average, an observation is going to differ about 2 points from the mean if there's a standard deviation of 2. All right. Let's look at a tangible example of some of this. Hopefully, this will help to illustrate the mean and the standard deviation in a useful way. So I have data right here on the teacher turnover rate in different school districts in Texas. I don't remember exactly which year of data I grabbed for this example, but it's a single year of data in Texas, and it's showing what percentage of teachers turned over, left their job within the year for that school district, or by the next year that they had left. So each observation, each row of data is going to be one school district, and we have different values for what the teacher turnover rate might be. So in one school district, it might be that they have a turnover rate of 20%. Another school district could have a turnover rate of 30%, right? And that's what's being plotted, is what those different values are here. And we learned about different types of graphs in the last lecture. This is one of those types of graphs that we went over briefly at the end, a kernel density plot. But here, we now see two different kernel density plots. We see the one that is dashed red line and then the solid blue line. So two different kernel density plots. And at the bottom of our graph, we see a legend that tells us what those two different lines are. They're two different distributions. So the solid blue line represents charter schools, while the dashed red line represents traditional school districts. So what's one of the first things we notice when we look at this graph? Well, one of the first things that I notice is that it seems like the teacher turnover rates tend to be a little bit higher in the charter schools. And this is consistent with what we generally see in the education literature, I know, from having read some of that. So it's very typical that charter schools tend to have a little bit higher turnover rates than traditional schools. And in particular, if we try to figure out, what looks like sort of the middle point of this distribution shown in blue, it looks like maybe it's around 30, 35, something like that might be a good approximation for the mean or the median, or the mode, right? That it looks like it's somewhere around here. And indeed, I've actually calculated the mean, or used data to calculate the mean, and I saw that it was exactly 31, or not exactly. If we round, it's 31. So among charter schools, the mean or average turnover rate is 31%. What about traditional schools? Well, here we can see that the mean is 20%. Further down here. So again, this is just showing how visually we can see that it looks like charter schools tend to have a higher turnover rate. We can see that visually, and we can also see that in these statistics that we were just talking about. The mean or the average is higher for the charter school districts than the traditional school districts. What about standard deviation? This is a little bit harder maybe to wrap our minds around. We hear averages being talked about a lot just in newspapers and society, but standard deviations, that's not such a commonly described statistic, right? So what does it mean that the standard deviation is higher for charter schools than it is for traditional schools? 4 points higher. Well, if you recall, we just said that the one way to interpret the standard deviation is that it tells us how far the typical observation is from the mean. So, in other words, I would say yes, the mean, the average charter school district has a turnover rate of 31, but there's a lot of variance around that because the typical observation is around 14 percentage points away from the mean. And you can see that visually here, that it's very spread out, right? There's lots of school districts that have observations around 10 to 20% turnover among the charter school districts, lots that are in this range of 40 to 60. And I say that there are a lot because this kernel density line is still very fairly tall. It's far away from zero. And so we can see this is very spread out, right? There's lots of charter school districts that have very low levels of turnover and also a lot that have really high levels. So there's a lot of differences among the charter school districts in terms of their turnover rates. When it comes to the traditional school districts, yes, there's still some differences, right? Some districts with, up to almost, and around 40% turnover rates, that's quite high. There's also districts with really low turnover rates. But overall, this is not as big of a range that we see the schools typically falling in or the school districts typically falling in for the traditional schools as the range of typical values that we're seeing for the charter schools. In other words, there's less variance for the traditional schools, which is why they have a smaller standard deviation. So hopefully, this visual example helps to cement for you what the meaning of the standard deviation is. Traditional schools have a lower standard deviation, and therefore it's a little bit more compact, the distribution of values compared to in the charter schools. All right, that's it for part one. And in part two, we'll be talking about transformations.